Okay, in this lecture we're going to cover our section 12.2 material on the second derivative. So in our chapter 11 work, we were working with finding the first derivative of a function, which gives us the rate of change of that function, or the slope of the tangent line to the graph of that function at a point. And we saw that the derivative of a function is itself a function. Therefore, we could find the derivative of the derivative, and this is something known as the second derivative of a function. It would be defined as the derivative of the first derivative. Now, the notation that we use for the second derivative is the following. We can use either f double prime of x, so we were using f prime of x for the first derivative, so we can use a double prime for the second derivative. Or using a Leibniz notation, we could say we are differentiating the function f prime of x, so that is differentiating the function df dx. So we could also rewrite this notation as d squared f over dx squared. So these would be two different notations we could use for our second derivative. Now, the second derivative of a function is, again, a function, so we could similarly define the third derivative of a function f as the derivative of the second derivative. And this would be denoted as f triple prime of x, or the derivative, d over dx, of the second derivative, d squared f over dx squared, which would give us d cubed f over dx cubed. So, of course, we can continue this process to define other higher order derivatives, say the fourth, fifth, sixth, and so on. And in general, we would denote the nth derivative by using the notation f with a superscript. In parentheses, we would have the number n of x. So typically, once we get up to the fourth derivative, we wouldn't want to use the prime notation anymore, because we'd have to have 4 primes. So if we start talking about, say, the 100th derivative, well, we don't want f with 100 primes, but we would use this notation where we write the order of our derivative in the superscript of our function. So let's look at some examples of finding higher derivatives of functions, and then we'll talk about some applications. So in this first example, we are asked to find all higher order derivatives of the function f of x, which is this polynomial. So let's start by finding our first derivative. So differentiating term by term, we have f prime of x is 4x cubed minus 9x squared plus 10x to the first plus 16. So then to get our second derivative, f double prime of x, we would differentiate the first derivative, f prime. So again, taking the derivative term by term, we would have 12x squared minus 18x plus 10. So then to find our third derivative, f triple prime of x, we would differentiate the second derivative, which gives us 24x minus 18. And then continuing to find our fourth derivative, this is typically where we change notation from primes to this superscript notation. So our fourth derivative of f would be 24. And then our fifth derivative of x, well, the derivative of any constant is 0. So our sixth derivative would be the derivative of 0, which is a constant. So the sixth derivative would also be 0. And then differentiating 0, we would keep getting 0 as all of our higher order derivatives. So we could write this as follows. The nth derivative of f is equal to 0 for all values of n greater than or equal to 5. So that is our fifth derivative, and all of the higher order derivatives will be 0. So here we have found all of the higher derivatives of this function. So let's consider another example of that. In our next problem, we are asked to find all higher derivatives of the function 1 over x, which to differentiate we may prefer to write as x to the negative first power. So finding our first derivative, f prime of x, using the power rule, we would have negative x to the negative 2, and our second derivative, f double prime of x, would then be positive 2x to the negative third, again using the power rule. So our third derivative, f triple prime of x, is equal to negative, and I'm going to write it in this way. Instead of saying negative 6, I'm going to write this as negative 3 times 2, x to the negative fourth. And we'll see why I'm writing it that way in just a moment. So continuing, if we find our fourth derivative, we would have a positive 4 times 3 times 2, x to the negative fifth. And looking at one more, our fifth derivative would be equal to negative 5 times 4 times 3 times 2, x to the negative sixth. So we start to see a pattern emerging when we're looking at these higher order derivatives. So let's see if we can come up with an expression for any derivative. Let's say the nth derivative of our function. So we'll start with the sign of our derivative. We saw that the first derivative, f prime, was negative. Our second derivative, f double prime, was positive. Our third derivative was negative. The fourth derivative was positive. The fifth derivative was negative, and this pattern will repeat. The sign will continue to alternate. So we see that all of the odd numbered derivatives, that is the first, the third, the fifth, the seventh, and so on, all have a negative out in front. So to capture that alternating sign, we could take negative 1 to the nth power, so that if n is an odd number, we get negative 1, and if n is an even number, we have a positive. Now the next thing that we can take a look at is the constant that appears in front of our variable x. So for the first derivative, we had a 1. For the second derivative, our constant was 2. For the third derivative, we had 3 times 2. For the fourth derivative, we had 4 times 3 times 2. And for the fifth derivative, we had 5 times 4 times 3 times 2. So in general, the pattern that's emerging for the nth derivative would be that we have a constant of n factorial. So recall that n factorial is used to denote the product of all of the integers starting with n and then decreasing by 1 until we reach the integer 1. So for instance, 4 factorial would be the product 4 times 3 times 2 times 1. And we see that this is the pattern that's emerging for that constant. So in general, for our nth derivative, we have a constant of n factorial. And the last thing we'll look at is our power of x. So for the first derivative, we had x to the negative second. For the second derivative, we had x to the negative third. For the third derivative, it was x to the negative fourth. For the fourth derivative, x to the negative fifth. and for our fifth derivative, x to the negative sixth. So in general, we have x to the negative in +1 power. The power of x is always 1 greater than the order of the derivative, and then made negative. Or if we wanted to rewrite this expression as a quotient, this is the same as -1 to the nth times n factorial over x to the positive n plus 1 power. So once we have this expression for the nth derivative, we have an expression for all higher derivatives. If there's any specific number derivative that we want, say the 1,000th, we could plug in 1,000 for n, and that would be our 1,000th derivative. So let's look at some other examples, maybe combining some rules or techniques of differentiation that we talked about in chapter 11. So in this next example, we have the function f of x is x times e to the x, and we're asked to find the 20/20th derivative of that function. So of course we wouldn't want to take 2020 derivatives, but we could start looking at the first few derivatives of this function and see if we could establish a pattern, as we did in that last example. Now in this example, our function f of x is a product, x times e to the x, so we'll have to make use of the product rule. So to get our first derivative using the product rule, we first take the derivative of x, which is 1, times the second function, which was e to the x. And then we add the first function, x, we leave alone, and multiply by the derivative of the second function. Now the derivative of e to the x is e to the x. And to simplify a little bit, I can factor out an e to the x from each term, and I'm left with 1 plus x. So let's look at our second derivative, f double prime of x. Well, we're differentiating f prime, which is again a product of two functions. So using the product rule, we start by differentiating the first function. So the derivative of e to the x is e to the x. And then we leave the second function alone, 1 plus x. Then we add the first function, which was e to the x, left alone, times the derivative of the second function. So the derivative of 1 plus x is 1. And again, if I factor out an e to the x from each term, I'm left with, altogether, 1 plus x plus 1, or 2 plus x. So finding my third derivative, we start to see a pattern emerge for the third derivative, again using the product rule to differentiate f double prime. We start by taking the derivative of the first function, e to the x, which is e to the x, times our second function, left alone, 2 plus x. Then we add the first function, left alone, e to the x, times the derivative of the second function. So the derivative of 2 plus x is 1. And again, factoring out an e to the x from each term, I'm left with 2 plus x plus 1, or 3 plus x. So looking at our first three derivatives, we start to see a pattern emerge. You can keep finding the next few if you want to verify the pattern. But in general, it can be seen that the nth derivative of this function is given by e to the x times n plus x. So if we want the 20/20th derivative, we would have e to the x times 20/20 plus x. So once we establish that general pattern, we can find an expression for any higher derivative, and then to get a specific higher derivative, we can evaluate our expression at that given value of n. So let's look at another one. In this next example, we are asked to find the second derivative of the function f of x, which is a rational function, a quotient of two polynomials. So to find our first derivative, we're going to have to use the quotient rule. So the quotient rule says we first take the derivative of the numerator, x plus 2, which would be 1, and then multiply by our denominator, 5x minus 1. Then we add the product of our numerator, x plus 2, times the derivative of the denominator, which would be 5. And then the entire expression is divided by the denominator, 5x minus 1 squared. So simplifying a little bit, if we distribute through the numerator, we have 5x minus 1 plus 5x plus 10 all over 5x minus 1 squared. And let's see, I've got an incorrect sign here. For our numerator, we're subtracting that second value for the quotient rule. So here, when I distribute, this should be a negative 5x minus 10. So simplifying, we have a 5x and a minus 5x, which cancel, and then a numerator of negative 1 minus 10, or negative 11, over 5x minus 1 quantity squared. So this is our first derivative, and to find our second derivative, we need to differentiate this function. And in order to make it a little bit easier, I might rewrite this as negative 11 times 5x minus 1 to the negative 2 power in order to avoid using the quotient rule. So now, using the chain rule to find my second derivative, since this is a composite function, in particular we're using the generalized power rule, well, I would take my power of negative 2, bring it out in front, multiplying by the negative 11 would give me a positive 22, times 5x minus 1 now to the negative third. And then we have to multiply by the derivative of this inner function by the chain rule, which would be 5 here. So rewriting this, we have our constant 22 times 5 would be 110. And then the 5x minus 1 to the negative third, we can think of as division by 5x minus 1 cubed. All right. So these last two examples illustrating where we might use, say, product, quotient, or chain rules in evaluating higher derivatives. So let's consider next an application or one interpretation of the second derivative of a function. So this application is going to be primarily a physics application. So let's say that we have some object, maybe a car, which is moving along a straight line, so some straight portion of road, and its position function is given by s of t. So its position, say, at time t. So we know that the rate of change of position, how fast an object is changing position, is called velocity. And we had introduced in our chapter 11 material the velocity function v of t as the rate of change or the derivative of our position function, that is s prime of t. So if we think about a second derivative, that would represent the rate of change of the first derivative, which was velocity, and the rate at which an object is changing its velocity is called acceleration. So we would define an acceleration function, a of t, as the derivative of velocity, or the second derivative of the position function. So let's consider an example of this. In this next problem, we are supposing that we have some object moving along a straight line, and its position in feet at time t, measured in seconds, is given by the position function s of t. So in part A, we are asked to find both the velocity and acceleration of this object at any given time. So to find velocity, v of t, we would be looking for the rate of change, or the derivative of our position function, which would be 9t squared minus 12t plus 8. And here, since position was measured in feet and time in seconds, this would be measured in feet per second. So then our acceleration function, a of t, would be the derivative of the velocity function. So we would have 18t minus 12. Now velocity was measured in feet per second, and then we're looking at the rate of change of that quantity with respect to time, which was measured in seconds. So we would have units of feet per second, or feet per second squared. So in part B, now that we have these functions, we're asked to find the velocity and acceleration of the object at time t equals 2, so after 2 seconds. So to get our velocity at t equals 2, we're going to substitute t equals 2 into the velocity function we found in part A. So we had, for that function, 9 times t squared. In this case, 2 squared is 4, minus 12 times t, which is 2, and then plus 8. So we have, let's see, 36 minus 24 plus 8, so that would be 12 plus 8, or 20. Again, we're measuring in feet per second. So 20 feet per second for the velocity after 2 seconds. And for the acceleration after 2 seconds, we would have 18 times t, which is 2, minus 12. So that is 36 minus 12, or 24, measured in feet per second squared. So one physical interpretation of the second derivative is as acceleration of an object. The second derivative of position would be the acceleration of our object. So let's think about a graphical or geometric interpretation of the second derivative. So here we can ask the question, what does the second derivative, f double prime, tell us about a function? So the second derivative tells us information about the concavity of a function. So much like the first derivative told us whether a function was increasing or decreasing, the second derivative will give us information about the concavity of the graph of that function. So let's introduce this in a bit more detail. In particular, if the second derivative of a function is positive for each x in some interval, that means the function f is concave upward on that interval. And if f of x is f double prime of x is less than 0 for each x in an interval, that means the function f is concave downward on that interval. So what exactly do we mean by concavity here? Well, we can think of this as sort of an upward opening or downward opening curve. So for instance, in these figures that I've given in the notes, in this left-hand plot, we're looking at the graph of the base e exponential function, y equals e to the x. And we see that our first derivative, e to the x, is always positive. So for any point that I choose on this curve, my tangent line to the curve is or has a positive slope. Therefore, the first derivative would be positive. Our function is increasing for all values of x. Now, if we look at the second derivative, which would also be e to the x, we're looking at the rate of change of the first derivative. So let's think about what that represents geometrically. So the slopes of these little tangent line segments, which I've drawn, represent the first derivative. And we see that as we move from left to right along the x-axis, these slopes are getting larger and larger. So that is the rate of change of the derivative is increasing. So the second derivative, f double prime of x, is also positive. Not only is our function increasing, but it's increasing at an increasing rate. Now, a counter or an example to illustrate, so we would say that this curve is concave upward. It looks sort of like an upward shaped bowl over that interval. Now for an example of a function being concave downward, let's look at this right-hand figure, which is the graph of the sine function. So in our course, we're not really working much with trig functions at all, but just to demonstrate an example of concavity, we could consider this sine x function. And we see that on the interval from 0 to pi, or from 0 to pi over 2, our tangent line has a positive slope. However, we start to notice that as we're moving from left to right on that interval, the slope of the tangent line is decreasing. So we see our tangent line starting to flatten out as we move from left to right. So the derivative is decreasing, which means that our second derivative would be negative. So here we have an example where on that interval, our function is increasing. So the first derivative is positive, but since the tangent line's slope is decreasing, that means the second derivative, or the rate of change of that first derivative, is negative. And we would say here that our curve is concave downward. It's sort of like a downward opening bowl. And we see, of course, if we were to keep moving past pi over 2, well, at that point, our tangent lines become or have a negative slope and start to get larger and larger in the negative direction. So this is what we refer to as a concave upward function or a concave downward function over an interval. Now, a little more terminology to go along with this. We would say, let me choose a different color here. We would say that a point where a curve changes its direction of concavity, that is from concave upward to downward or from downward to upward, is called an inflection point. So in our right-hand plot here, clean up my graph a little, we see that our function appears to be concave upward on the interval from negative pi to 0. It's sort of like an upward opening bowl. And then from 0 to pi, our function appears to be concave downward. It looks sort of like a downward opening bowl. So this point, in this case 0, 0, where we changed from concave upward to concave downward, is referred to as an inflection point. All right. So let's look at some examples of determining the intervals of concavity or inflection points for a function, and then we'll consider some applications. So much like we saw in section 12.1, where we were asking for the intervals on which a function is increasing or decreasing and where it has local extrema, the second derivative, or the sign of the second derivative, will tell us the intervals on which a function is concave upward or downward, and tell us where the inflection points are. So in these next two problems, we're asked to find those intervals on which the given function is concave upward or downward, and then find any points of inflection. So in part A, we have f of x is this polynomial, and for concavity, we need our second derivative. So let's start by finding the first derivative, f prime of x, which is 18x squared minus 48x plus 9. And then the second derivative, f double prime of x, is equal to 36x minus 48. So to determine where the second derivative is positive or negative, we first need to determine where it's equal to 0. Where is it neither positive nor negative? So here we have 36x is equal to 48. So x is 48 divided by 36, or dividing top and bottom through by 12, that reduces to 4/3. So much like we had for the increasing-decreasing test, we can think about the domain of our function here. So for a polynomial, all real numbers, x. And we had a value of x equals to 4/3, where our second derivative was 0. So that means everywhere else, that is to the left or to the right of 4/3, the second derivative must be positive or negative. And to determine the sign, we can choose a test value of x in each of those subintervals. So for instance, to the left of 4/3, we might choose x equals 0, and then substituting x equals 0 into the second derivative, we would have a negative 48, which means that our function is concave downward on that interval. Now choosing a test value of x to the right of 4/3, we could take maybe 2 or any number greater than 4/3, and substituting into the second derivative, we would have 72 minus 48, which is a positive number. So our function is concave upward on that interval. So summarizing our answer so far, we would say that this function is concave upward on the interval from 4/3 to infinity, and is concave downward on the interval negative infinity to 4/3. So we were also asked for points of inflection. So for an inflection point, remember that was points where we changed the direction of concavity. So we saw from our work so far that this function changed concavity when x was equal to 4/3. So the x-coordinate for our point will be 4/3. And then we have to find the y-coordinate. Since we're asking for an inflection point, that means both the x, y coordinates for a point. So to get the y value corresponding to this x value, we would take our value for x, which was 4/3, and substitute into the original function. So plugging in 4/3 for x in this function, you see that we have a negative 148 over 9 for that y-coordinate. So a little bit difficult to simplify by hand, but you can make use of a calculator to find that y value as well. So we have the following results for that function. And in part B, we have a similar problem. F of x is this fourth degree polynomial. Again, we're asking for intervals of concavity and points of inflection. So let's start by finding our first derivative, f prime of x, which would be 4x cubed plus 24x squared plus 36x plus 12. And for our second derivative, f double prime of x, we have 12x squared plus 48x plus 36. So for intervals of concavity, we need to know the sign of the second derivative. So first, we want to find the values of x for which the second derivative is neither positive nor negative. That is where it's 0. So to solve for x, we could first divide this equation through by 12. So we would have 1x squared plus 4x plus 3 is equal to 0, which then factors as x plus 1 times x plus 3 is equal to 0. So we have two values of x, namely -1 and -3, which make the second derivative 0. So to determine our intervals of concavity, let's think about the domain of this function. So for a polynomial, all real values of x, and we had x equal -3 and -1 as the values for which the second derivative was 0. So to determine the sign of the second derivative in each of these subintervals, we're going to choose test values for x in each subinterval. So say to the left of -3, we might choose -4. And substituting -4 into our second derivative, or the simplified form of our second derivative, while plugging in -4, we see we would have a negative number times another negative, which means that our second derivative would be positive on that interval. Now between -3 and -1, a good choice might be -2, and substituting -2 into this second derivative expression, we would have a negative times a positive, which would give us a negative for the second derivative. And then to the right of -1, we could choose, say, x equals 0. Substituting into our second derivative, we get a 36, which is, of course, positive. So we would say that our function is concave upward on the intervals from -infinity to -3, or from -1 to infinity, and is concave downward on the interval from -3 to -1. So for our inflection points, those are the points at which we change concavity. We saw that we had x could be -3 or -1. And to find the corresponding y value for these x values, we would take -3 or -1 and substitute back into our original function. So if we take -3 and substitute into this function, we find a value of 339 for the y coordinate. And if we substitute -1 into this function, we have a -85. So this would be our results for part B. So as a geometric interpretation, the second derivative tells us the concavity, or the shape of the graph of our function. Is it opening upward or downward? So now let's consider some applications of concavity. So in this next example, we're told the revenue measured in millions for Sirius XM satellite radio can be approximated for the period 2004 to 2015 by the revenue function R of X given here. And we have a restriction on the values of X. This is only valid for X equals 4 to 15. So where X equal 4 corresponds to the year 2004. So here from 2004 to 2015, that's why we're cut off at 4 and 15 here. We're told it can be shown that this revenue was increasing throughout this period. And the question is to find the intervals over which the revenue function is concave upward or downward, and then find any points of inflection, and then interpret our answers in practical terms. So just like the previous example, to find intervals of concavity, we need our second derivative. So starting with the first derivative of our revenue function, or the marginal revenue, we would have negative 12x squared plus 216x minus 440. And then our second derivative, r double prime of x, is negative 24x plus 216. So to determine where our second derivative is positive or negative, we need to first find the values of x for which this is 0. So this would give us 24x is equal to 216. So dividing by 24, x is equal to 9. So thinking about the domain of our function, in this case we had a restricted domain. X could only range from 4 to 15. So we have 9 within that domain. And we need to determine the sign of that second derivative on these two subintervals, to the left of 9 and to the right of 9. So to the left of 9, we could choose a value, say x equals to 8, and substituting into our second derivative, the value x equals 8, we would have a positive value for the second derivative. Now to the right of 9, we could take, say, x equals 10, substituting into the second derivative, we would have negative 240 plus 216, which is negative. So based off of our work so far, we can say that this function, which represents revenue, would be concave upward on the interval from 4 to 9, and concave downward on the interval from 9 to 15. We were also asked for points of inflection. So for an inflection point, we saw that we changed concavity at the value x equal 9, and then substituting 9 into the original revenue function, r of x, we get the y coordinate for that value. So here, substituting in 9 for that function, we get a value of 2,172. But remember, that was being measured in millions. So 2,172 million if we're thinking about the actual revenue value. So for our interpretation of this answer in practical terms, we could say, well, on the interval from 4 to 9, so that is in the time period from 2004 to 2009, the revenue was increasing at an increasing rate. So recall, the second derivative measures the rate of change of the rate of change of our function. So our revenue was increasing, and since the curve was concave upward, the second derivative is positive. That means it was increasing at an increasing rate. And from 2009 to 2015, the revenue was increasing at a decreasing rate. So if we consider this problem more generally, we see that this illustrates a principle known as the law of diminishing returns. So let's explain this in a little more detail. So we say that the law of diminishing returns is a concept in economics which is related to concavity. So let's sketch below the graph of a function f showing the output of a function y equals f of x from a given input x. So for instance, something similar to maybe what we had in the last example, where our input could be advertising costs, that is how much we're spending on advertising, and the output would be the corresponding revenue from sales. So to illustrate this idea, suppose that we have the graph of a function in the xy plane, where our x-axis is the input, maybe advertising costs, say in dollars, and the y-axis would be our output, maybe revenue from sales, also measured in dollars, or could be, say, millions or thousands of dollars. And we might have a curve that looks something like this. So here, y is some function of x. And we see that for this curve, it appears to be concave upward from x equals 0 until x equals c. So it looks like from our sketch that our curve is concave upward on that interval, and then it changes to concave downward once x becomes greater than c. So we have some corresponding y value f of c, so this point, which is an inflection point where we change concavity, would be c f of c. So our graph here is illustrating an inflection point at the point c f of c, and for values of x less than c, the graph of our function is concave upward, which indicates that our output, say revenue, is increasing at a faster rate with each additional dollar spent. However, when x becomes greater than c, the graph is concave downward, and the increase in our revenue, y, is smaller with each additional dollar spent. So once we get past an advertising cost of c, each additional dollar that we spend on advertising does not result in as large of an increase in revenue. Therefore, further input beyond c dollars produces diminishing returns. So this inflection point on our curve would be called the point of diminishing returns. We would not want to exceed advertising costs above that level. So let's consider an example of this. Here we are given a revenue function, r of x, and we're told that this function is representing revenue in thousands of dollars, where x represents the amount spent on advertising in thousands of dollars. So we want the point of diminishing returns, which is an inflection point for this curve. So we need to find our second derivative. So starting with the first derivative, r prime of x, we have 72x minus 3x squared. And so our second derivative, r double prime of x, is 72 minus 6x. So to determine where we might change concavity, say from positive to negative or vice versa, we would set this second derivative equal to 0. And we have 72 is equal to 6x, and so x is equal to 12. Now we need to ensure that we actually change concavity at that point. Remember, just because the second derivative is 0 doesn't necessarily mean that you've changed concavity at that value. So if we consider the domain of this function, say from, so if x represents dollars spent, could not be less than 0, but we could spin infinitely large. And we found that at x equals 12, we had a second derivative of 0. So to determine the concavity to the left of 12, we could choose a test value, say x equals 11, and substituting into our second derivative, we would have 72 minus 66, which is positive. So our function is concave upward there. And to the right of 12, we could choose, say, 13, and substituting into our second derivative, we have a negative value for the second derivative. So it's concave downward. So we see that we do change from concave upward to downward at x equals 12. So here we would say the point of diminishing returns is the point where x was equal to 12, and then substituting 12 back into our revenue function for x, we get a y value of 44.56. So let's think about what that represents here. So these values of x were measured in, represented the amount spent on advertising in thousands of dollars. So this illustrates that we would not want to exceed $12,000 in spending on advertising. And if we spend up to $12,000 on advertising, we could expect our revenue to increase to a value of 44.56, but that was being measured in thousands. So we could expect our target amount spent on advertising would be $12,000, and the corresponding revenue from sales would be $4,456,000. Now, in the last part of this section, we'll consider an application of the second derivative in determining whether a function has a local maximum or a local minimum at a critical point. So we had a result known as the first derivative test, where we used f prime to determine whether a function had a maximum, a minimum, or neither at a critical point. And we have a similar test known as the second derivative test to tell us whether a function has a local max, min, or neither at some critical value. So here's what it says. Suppose that a function has a critical value of c, and f prime of c is 0. And the second derivative, f double prime, is continuous on some interval containing c. So this second derivative test has one of three results. The first result is if the second derivative of our function at the critical value is positive, that means that f has a local minimum at that point c. Let's think about geometrically why that would be true. So if we had some function, and let's say this graph looks something like this. So graph is y equals f of x, and we have a critical point or a critical value at some value c. That is where we would have a point on our curve with a horizontal tangent. So if, as part one of this theorem says, if the second derivative of our function at that point, c, is positive, that means our function is concave upward there. It has this sort of upward opening bowl shape. Therefore, that critical value would be the lowest point on our curve. Now, the second part of this theorem says if we have a second derivative which is negative at a critical value, then f has a local maximum at that critical value. So to illustrate, if we took a separate value for c, where we have a horizontal tangent, and we see that the second derivative there is negative, so that is our curve is downward opening, that means that that critical value must yield a maximum. Now, in the case that the second derivative is equal to 0, then this test would be inconclusive, and we would have to make use of the first derivative test instead. So let's look at some examples making use of this new theorem. So in our next example, we're asked to find all the critical values of this function f of x, and then use the second derivative test to determine whether it leads to a local maximum or minimum. So first, to find the critical values of this function, we're going to find our first derivative, f prime of x, which is 4x cubed minus 64x. And this function is defined everywhere, so the only critical values we could have would be values which make this derivative 0. So to solve for x, we could factor out a 4x from each term, and we would be left with x squared minus 16 is equal to 0. And then that quadratic can be factored as x plus 4 times x minus 4. So we have three options for x here. Either x is equal to 0, x is equal to negative 4, or x is equal to positive 4. So these were the critical values. Now, once we find these critical values, the second part of the question says use the second derivative test to determine whether these values lead to a local maximum or minimum. So we need to find the second derivative, f double prime of x, which here is equal to 12x squared minus 64. And then we're going to evaluate the second derivative at the critical values we found. So let's start with f double prime of 0. So here we would have a value of negative 64, which is negative. So that means our curve is concave downward at that critical value, which implies from the second derivative test that we have a local maximum at the value x equals to 0. So let's look at our next critical value. If we take a look at f double prime of negative 4, we get a value of 128, which is of course positive. So our graph is concave upward at that critical value, which implies that we have a local minimum at x equals negative 4. And then for our last critical value, f double prime of 4, we again have 128, which is positive, again implying that we have a local minimum at the value x equals 4. All right. So in our last example, we have the price of Starbucks Corporation stock for the years 2003 through 2015 can be approximated by this polynomial f of x, where x is restricted here. So since we're only considering 2003 through 2015. X has to range from 3 to 15, where x equals 3 corresponds to 2003. So in part A, we're asked for the critical values of this function. So again, we're going to find our derivative, f prime of x, which is equal to 1/2 x squared minus 7x plus 45 halves. Now this function is defined everywhere, so the only critical values we would have are values which would make this derivative equal to 0. So here, to start, I don't like the fractions that I have in this polynomial, so the 1/2 x squared or 45 halves. But if I multiply both sides of this equation by 2, I can get rid of those fractions, and I would have x squared minus 14x plus 45 equals 0. And now this can be factored as x minus 5 times x minus 9 is 0. So we find that x could be equal to 5 or 9. These would be our critical values. Now in part B, we're told again to use the second derivative test to determine in what years the price was at a local maximum or minimum. So we need to first find the second derivative, f double prime. So differentiating the expression that we had for f prime in the first part of the problem, our second derivative would be 1x minus 7. And now we are going to evaluate the second derivative at the critical values we found in part A, namely 5 and 9. So evaluating f double prime of 5, we have 5 minus 7, or negative 2, which is of course less than 0, which means that our function is concave downward at that point. So we have a local maximum at x equals to 5. And evaluating the second derivative at 9, we have 9 minus 7, which is positive 2, which means the graph of our function is concave upward at that point. And so we have a local minimum at x equals to 9. So we could say here that the stock price is, or let's say was, a maximum at x equals 5, which corresponded to the year 2005, and a minimum at x equals 9, or in 2009.